In this video, we will start our discussions on time and space complexities. Any programming task can be divided into two phases. First is the problem-solving phase, in which we look for a proper way of solving the problem. By proper way, we mean the sequence of steps required to solve the problem. And while doing this, we also focus on solving the problem efficiently. This ordered sequence of steps to solve a problem is known as an algorithm. Once the algorithm is determined, we can implement it using any programming language. As an analogy, think that the problem we are dealing with is making black tea. We know the sequence of steps for this problem. First, we boil water in a pot, then we put some tea leaves into it, and next, we stop boiling and cover the pot with a lid and keep it aside for 2 minutes. After 2 minutes, we use a filter to pour the black tea into a cup. Note that here the sequence of steps is very important. If we use the filter before putting the tea leaves, we will get only hot water. Once we know the sequence of steps to make black tea, we can use any device to make it, for example, gas, stove, or induction oven. Here, the sequence of steps to make tea refers to the algorithm to make tea, and the device is equivalent to the programming language used to implement the algorithm. As we said before, we always look to develop efficient algorithms, that is, algorithms which will take less time and space to execute. While the meaning of less time is understandable, what do we mean by less space? Basically, when we write a program corresponding to an algorithm and execute it, some space is occupied in the RAM by the variables used in the program. If we avoid using redundant variables or write the program in such a way that it requires less number of variables, then we can actually save some space in the RAM. Sometimes while writing programs using arrays, we also need to use additional data structures like stacks and queues whose length is proportional to the size of the input array. If the array size is very large, say 4,000 bytes, then we require another 4,000 bytes or more for the stack or queue. While today, due to the availability of high-end RAMs like 8 gigabytes and 16 gigabytes, space is no longer a constraint. It is always advisable to write algorithms that are efficient both in terms of time and space. A very important point to note here is that analysis of algorithm also helps us understand how practical would it be to use a particular algorithm if the input size is very large. Algorithm analysis can be done at two different stages. A priori, that is before implementing it, and a posteriori, that is after implementing it. First, let us understand what a posteriori analysis is. This analysis is carried out after running the program on a target machine. Through this, we can check the actual running time or space taken by the program to execute. However, this analysis is also system-dependent. If the same program is executed on a faster machine, it will take a lesser time to execute. The question is, can we quantify the running time or space of an algorithm in a way that is independent of the system on which the program is executed? Fortunately, there is a way which is called a priori analysis. Even without running the program, we can measure the efficiency of an algorithm just by going through the algorithm steps. Thus, this type of analysis is independent of processor speed, RAM, programming language, or other factors, and is usually measured in terms of the number of inputs to the algorithm. For example, if the input to the algorithm is an array of size n, then through a priori analysis we can derive the running time or space taken by the algorithm in terms of n, that is n or n square or n cube or log n, etc. The expressions that we derive are called time complexity and space complexity of an algorithm. To summarize, consider an algorithm takes n different inputs. Its efficiency is measured in terms of time complexity and space complexity, both of which are measured in terms of n. That is the number of inputs to the algorithm. Suppose an algorithm takes time 5n squared plus 7n plus 8. Since we should always think of an algorithm's performance for very large n, we will say that the algorithm takes time of the order of n squared, since for very large n squared term will dominate rest of the other terms. A similar discussion can be made for space complexity as well. Now, suppose two algorithms, say algorithm 1 and algorithm 2, to solve the same problem take time of the order of n squared and n, respectively. Then algorithm 2 is more efficient than algorithm 1 in terms of time complexity. Thus, A priori analysis helps us understand the efficiency of an algorithm without actually implementing it on a specific computer. This, in turn, helps in comparing different algorithms developed for the same task and choose the most efficient one. Thank you.